So we are going to the third way of the initial feasible solution. If you compute the initial feasible solution using the Borges approximation model, and this is based on the concept of the penalty cost or the regret. Okay, if you do that, you are going to get an initial feasible solution, which is 5,125. And that will be less than the northwest corner rule, just like the minimum cell cost. Okay, now 5,125 is definitely going to be less than the minimum cell cost, because the minimum cell cost approach was as you can see here, it was 4,550. Okay, so you can see clearly that it is in between the northwest corner rule and that. We are not going to calculate it. We're not going to calculate the Borges approximation, but you can learn that on your own. Okay, but we are now going to go ahead and then arrive at the optimal solution using the stepping stone method. Remember, there is a stepping stone method and the modified distribution. We're not going to do the modified distribution. We are just going to do the stepping stone method so that we have optimal feasible solution, not just initial feasible solution. Okay, so what is a stepping stone method? What is it? Well, after getting the initial feasible solution, the next is to solve for the optimal. We know this. That is the true lowest cost using this approach. Okay. Now, because the initial feasible solution that we obtained using the northwest and then out of all that, the minimum cell cost was the lowest one. Okay, that's what we are going to use to demonstrate the stepping stone solution method. That's what we're going to use to demonstrate the stepping stone solution. So let's start with that. Okay, recall the minimum cell cost method. The value, the profits, the total cost was 4,550. That was the total cost that we had there. Okay, so keep that in mind. So we are going to build on that total cost premises. Okay, and this is the approach that gave us that. Now, the key point in the stepping stone method is this. When you look at the transportation model itself, okay, our goal is to find a route, a transportation route, which is not currently being used. An empty cell, okay, but it would have led to a lower cost, a lower total cost if it were used. That is the whole principle. That is what the stepping stone solution method is checking. That there is, so when you look at it, is there a particular route which is currently not being used, but probably would have led to a lower cost had it been used? Because remember, what the minimum cell cost was doing was to allocate, but once you have already been allocated, there is nothing that can be allocated to you because it is going to conflict with the demand and all the supply instructions. And so there are some of them like 6 and 7. We did not touch them because, they will violate the demand requirement. And so the question now is, are there some routes that have not been used? Are there some cells that have not been used that could have actually yielded a lower cost? That is what a stepping stone is looking at. So I want us to look at those. I've even given you the answers. I want you to look at those cells. So which cells, first of all, which cells are empty cells? How many cells are empty cells here? How many of the cells are empty that you see? 4 cells. Okay. Now, the moment you say 4 cells, then I want to assume that you know what those 4 cells are. Okay. So the 4 cells are 1A, 2A, 2B, and then 3C. Okay. Those are the cells. Okay. Now, tell me which one will give us the lowest cost? Okay. When you look at them, which of these will give us the lowest cost? You don't need to raise your hand, just type the answer. Because this is a simple answer that you can give. Okay, it is 1A. Okay, it's 1A. Okay, the 1A is the one that will give us the lowest cost. So that's where we are going to start from. We're going to start from that 1A. Okay, because that's the one that, and look at how we start from there. This is what we do. Okay, we are going to assume that, because remember what we said was that you have to now act like you should have used that empty cell, but you didn't use it. But the possibility is that it could have yielded you a good thing. So what we are going to do is that we are going to add 1 ton. Okay, because remember we're having ton. We're going to add 1 ton, knowing the cost that is going to give us to that particular cell. And when we do that, we got to make sure that we balance it with the others. So if you should add 1 ton here, okay, we are going to have this whole cell 1A to have +1. And the moment you do that, on the right of the supply, you will see that the 150 will go up by +1. So you are now have the 150 go up by +1. But the moment you do that, because you have violated this section here, you have violated the 150. So it means that you need to do something on that row. Okay, you need to subtract -1 on that row so that it will balance. The 150 +1 will come back to 150. So if you add a +1 to this, which of these, of course, we can't go here. We are looking at this one first. Which of these, the 1B or the 1C, which of them do you think we need to subtract? Okay, that 1 ton from. And please remember, whenever you remove 1 ton, what it means is that you are removing a certain what? A certain cost. Whenever you add 1 ton, it means that you are adding a certain cost to it. And so looking at this, which area or which one should we remove the 1 ton from to be able to, satisfy the condition, okay, without violating any particular principle. So that is a principle that we are going to use. So to avoid the constraint violation and infeasibility, we must balance it by subtracting 1 ton on the row. Where do we minus that? Okay, so we've done the +1 here. Where do we minus that? Where do we do the +2? Sorry, the -1. Well, when you look at it, okay, it's the 25. Okay, so we got to do it at the 25. So you do -25 here. And why are we doing that? Why are we doing that? We are doing the -25 here because that will first of all balance by bringing us the 1 ton here. Okay, so we are removing 1 ton from this, and that will give us again a smaller cost. But you see, the moment you do the -1 here, you have affected this column B. You have affected it because straight away column B will now move from 100 to 99 tons. But then we need a total. And so while still in this column B, you need to do something. You need to do something significant, something interesting to this column, one of the tons there, so that you come back to 100. And which one do you do with? Whether it's here. Okay, the -B at 1B reduced by total cost of A, but reduces the 1 ton. And to compensate for that -1, we must add 1 ton to a cell that already has an allocation. Okay, so the most focused important thing is the cell must have an allocation. Please remember, we are not allocating empty cells. We are not allocating cells that were not allocated before. We are allocating cells that were already allocated. And you can see that this cell was already allocated than the 11. The 11 wasn't allocated at all. It's allocated cells we are dealing with. And so we now apply the +1 back to this. So we now add +1 to the 75, and then we balance this section. Okay. But once you do that, that also affects this column. So it means that now we have added +1 to this. So the whole of the 275 has now moved to what? Has now moved to 276. And so once again, you will have to now subtract -1 from this row 3. And that should be given to this one. Of course, not this empty, but this one. Now, why this one? Well, this one, because one, it is an allocated cell. And even if this one was not allocated, it will be the one with the lower cost. Okay. And once you do that and give this -1 to the 200, -1 ton to the 200, it will balance. Because remember, the 200, when there was a +1, okay, that reduced this one to 199. We didn't talk about it because we know that eventually we'll have to come and work out that. And so once you do -1 to this, the 200 now balances. So we're going to go through the process. The whole process is like crossing a pond, crossing a pond and then stepping on stones. Okay. Stones are the allocated cells. So you are stepping only on the allocated cells and you are stepping on stone. That is why the method is known as stepping stone. So you move from here, you go to that level there, you come down, you add +1 here, subtract -1 here, everything is balanced. Okay, so now how do you obtain the minimum cost now? Well, first of all, look at it. We are from 1A, we move to 1B. From 1B, we come to 3B. From 3B, we go to 3A. That's it. Okay, and the dollar amount there, we added +6 -8. We added +4, and then we did -4. So eventually, we have subtracted $1 from our costs, overall cost eventually. That have still balanced the thing. So overall, the total cost is reduced by $1. What this means is that for each ton allocated to cell 1A, so if you allocate 1 ton to cell 1A, which is a route that is not at present used, currently, that route is not used. If you allocate 1 ton to that, the total cost will reduce by $1, which is not bad because we want to find out that stepping stone approach idea is to find out whether we can move from feasible solution to optimal solution. So that moves us to an optimal solution because as long as your cost is coming down, that is said to be optimal. Okay. Now, you have to do that. We started with cells 1A. But you have to do that by starting also with all the other empty cells and going around the whole approach again and balancing. Okay, now I have done that, but you can do that later. But the key point is that after all the empty cells are evaluated one by one, okay, where you give it +1 and then see how the corners are not affected or are compensated, the one with the greatest cost reduction potential is the entering variable, is the one that becomes the useful one. That's right, the one with the greatest cost reduction. So you can see that 1A gave us a total cost reduction of -1, or total cost reduction of 1. What about the others? What about the others? Well, this is it. This is what we have. You will know that the X1A will give us, what is it? X1A, that is the one that gave us a total cost reduction that was good, that was powerful, that was sensible. Okay, so X1A, if you look at X1A, you have, remember 1 ton was there. X1A, the value of the tons that were there, you will notice that. So when you look at the X1A, that will give us 25 tons. 25 tons. Okay. X2C. And you can go and check S2C. Let's go and check S2C. Okay. S2C, the tons there is what? is 175. Okay, so that is 175 tons. Now, X3A is also 175. X3A. Okay. When you take that cell, you will also get 175, 275A. And so eventually what is going to happen is that you're going to do for each of these calculations, and then you will now slot them into the Z function, and that is going to give you a final value of 4,525. Now I want you to look at this value of 4,525 because I'm going to show you something. 4,525. Now when you come to the minimum cost, where is it? Okay. When you come to the minimum cost approach, that gave us 4,550. And so 4,425, you can see that the stepping stone method has given us a lower cost, which makes it an optimum solution.